Hello everyone, good morning. My name is Yannick Sztamfazer. Don't try to pronounce my name at home, it's not good. My supervisors are Joaquin Miguez from Teoría de la Señal and Manuel Sanjurjo, and yes, welcome to my doctoral meeting. So many of you may have heard of the collision that occurred in 2009 between the two operational spacecraft, Iridium 33 and Cosmos 2251. Essentially, they collided and they released loads of fragments into Earth orbit. And so this essentially prompted people to start worrying about this possible theoretical phenomenon called the Kessler syndrome, by which Earth orbit could at some point become inoperable because it would be filled with space debris and it would just be super hard to navigate safely. So we want to avoid this apocalyptic scenario, and there are three ways of doing so. There are many other aspects to deal with, but one of the important ways of dealing with it is to actively remove the debris if you're able to somehow locate it and deal with it. Another one is ensuring that there's space policy in place in order to have spacecraft decay after their orbital lifetimes are up. And three, and one of the main topics of this thesis, is to accurately track spacecraft and their uncertainty, and therefore ensuring safer navigation and avoiding collisions. So we can see the spacecraft or space debris space object number has been steadily increasing for the first pretty much 40 years of space exploration. And then you could say kind of skyrocketed. So basically you can see some peaks that are associated to particular events, such as the Iridium Cosmos collision that occurred that I just mentioned, but also you can see an increase in actual spacecraft number related to the deployment of mega constellations and like SpaceX's constellation and OneWeb and stuff like that. So the contents of my thesis are, for now, it's divided in three. The first topic is uncertainty propagation as applied to tracking spacecraft and methodologies in doing so. Second topic is computing the probability of collision by exploring new methodologies involving extreme event theory. And number three is stochastic propagation schemes, but applied to predicting the re-entry window of the spacecraft that's re-entering. Today, I'm only going to focus on this one because I only have 5 minutes, probably like 2 now or something. But essentially, we want to determine the state of the spacecraft, so its position, velocity, or the set of orbital elements that describe its position, and its uncertainty. So we want to be able to propagate this uncertainty forwards, and by using filters, then once we compute the trajectory, then we get an observation and we essentially adapt our knowledge of the system so we can, repredict the next part of the trajectory. So there are two main things that I want to tackle. One of them is that orbital dynamics are classically modeled in a deterministic fashion, which means that essentially the acceleration, so you model the spacecraft state by computing the acceleration felt by the spacecraft. And that's given by this term, by this equation here, where you have the gravitational pull and then you have a set of perturbations associated to the orbit that it's in, such as drag and so on and so forth. And deterministic modeling of this means that essentially you have no randomness in this equation. And this is not true because inherently in the system, there is some randomness that you can't really account for unless you have like absolute perfect models, but you don't. So we model them with stochastic differential equations by viewing it as by viewing the state as a random variable. So the way you reformulate the problem is by essentially having, you have the drift function here, which is essentially composed of the deterministic part that we saw earlier. And then you add a stochastic term, which is composed of the Wiener process, which is essentially just random noise added to the process. So with suitable numerical schemes, you can essentially create a way of dealing with the state at the current time and predicting the next time step. That's need number one. And need number two is, so uncertainty propagation methods commonly assume Gaussian uncertainty, which is a very efficient way of dealing with it. But at long propagation times and without measurements, these assumptions may break down and your estimation might deteriorate in quality. So you need methods which are able to approximate this distribution more accurately and therefore presenting less restrictions. So here's just some methods that I've been applying so far. So if we neglect the Gaussian ones, not because they're not good, just because it's not the topic of this, but we focus on the Monte-Carlo style methods, more particularly the particle filter, where essentially if your system is linear and Gaussian, then the posterior PDF, the probability density function associated with state, can be determined exactly with the Kalman filter, for example. But since our system is nonlinear and possibly non-Gaussian, then we aim to approximate this by the use of particle filters, as I said. So the way particle filters work, in a nutshell, is essentially you sample particles from a prior distribution, and you advance them through the state equations to the next time step. And then if you have an observation, then you weigh these samples based on how well these samples match the observation that you obtain. Then you essentially have a critical step called resampling, where you replicate the particles with high weights and you remove the ones with low weights. And you essentially repeat the process again by propagating to the next time step, and sequentially you are able to approximate this posterior more accurately. And this is essentially what we're doing now with the ESA project right now in conjunction with GMV. UC3M are essentially in charge of studying the applicability of particle filters and their suitability for different scenarios and such. And this is just a little summary of what I've been doing so far. I presented the results of section 2, which I didn't cover today because there's no time, at the ESA conference in January 23. And the aim is to validate those results and prepare for a journal submission, which is taking forever, but it will happen at some point, hopefully. Finished the pre-prototype for the ESA project. Just sent an abstract to the space-flight mechanics meeting in January 24, fingers crossed. And also preparing a possible research day at ESA Super in 24, if all goes well. That's it. Thank you very much.